confidence intervals. Okay, we're using them as a way of estimating the parameter called population mean, or mu. And in our previous work with population proportion, in a different series of videos, we did look at confidence intervals, and we looked at before that the difference between what's called a point estimate and an interval estimate. And while point estimates are very simple, a one-off single valued estimate, they're also very risky because the sample taken could be far from the mean. It could be non-representative of the mean. So interval estimates have some advantages. So in this video we're going to look at that in terms of not population proportion, but population mean and sample mean. And we'll make use of that confidence interval formula you can see on the screen at the moment. So one way of defining the confidence interval is it's an interval estimate for the population mean. Okay, it's the confidence interval for mu, the population mean. So it's basically saying we're reasonably confident that the interval contains mu, the parameter. Okay, so it's being reasonably confident, okay, and that can vary, as we've seen before, of confidence intervals. What's different about this way of looking at confidence intervals? Well, the way we're looking at it's not different, I suppose, but it's the statistics and the random variable we're looking at is based on different things of interest. So we're looking at, from our previous work on sample means and so on, we're looking at random variable x, capital X. We're looking at large enough sample sizes. Okay, the sampling distribution x bar is approximately normal. It's approximated by a normal distribution, which you've seen in several videos just preceding this. And this relates to the central limit theorem, and thus we can say the mean of the samples is equal to the population mean, provided those conditions are satisfied, and the standard deviation of the samples is the population standard deviation over the square root of the sample size. We've seen the standard normality too. So it's capital X bar minus mu over sigma over root n. So all of those things come into play with this. We're using the same quantiles for different levels of confidence. So 90% Z is 1.64, 95% Z is 1.96, and 99% Z is 2.58. By standardizing things and looking at the standard normal distribution variable Z, if we look at an example using the 95% confidence level, we know that the expression there, the probability from negative 1.96 to 1.96 for Z is 0.95. We can replace that with that expression for normality to do with sample means, and we can multiply through to get this next line. And you can see that we multiplied through to go from here to here, we multiplied through by sigma over root n. And then we further simplify and we get that expression at the bottom. Okay, and that's related closely to the formula. So in this case we have an expression which gives us an interval with 95% property will contain the value of the mean, the population mean. And we don't actually know what it is, but we have calculated there's 95% probability that that actual interval will contain whatever the mean is for the population. And while we don't know what the population mean mu is, usually also we don't know what the population standard deviation sigma is. So If the sample, however, is large enough, as a rule of thumb, at least 30, then we can use the sample standard deviation S. Alright, so that's important to note. So from that previous expression we had just here, we can find, by the way, I'm talking about sigma being used there. We often don't know that in practice. Sometimes it's assumed, occasionally we know it, but usually we don't know it, so we use S provided n is at least 30. So we can see that there's an S there now, and that's the confidence interval formula. Okay, it will provide two numbers separated by a comma to denote the interval, and we got Z times S over root n either side of the sample mean. Okay, and again, S is the sample standard deviation, N is, as usual, the sample size, and we know about the Z score for the level of confidence. So the Z will depend on what level of confidence we desire here. Future video is going to talk about this quantity here that links to what's called a margin of error and precision. Next video also will look at, next video or videos will also look at further interpretation of confidence intervals. This video is basically introducing the background, a basic derivation, and some worked examples to get us started, and then we can get into more interpretive type of tasks and so on. Now for some worked examples, and first of all here we have to find an approximate 95% confidence interval for the mean IQ of people doing first year stats major at uni in some country called A. Alright, if we select a random sample of 100 students and find the sample mean to be 108.6, alright, so we've got to find the confidence interval. Now this is unusual, but just to get us started, we're going to assume a standard deviation is 15, but that's not typical. Okay, it's usually this has to be some sample taken, and the standard deviation of the sample is has to be actually be done by taking the sample itself and doing the calculations. We're going to do that. Then we're going to repeat for n equals 400 and see what gives. Then after that, we're going to compare for the above sample, i.e. the n equals 100, the original one. We're going to see the effect of changing the confidence intervals. So we've got a few things to do here. So for the first part here, where we've got n equals 100 and we've got the 95th confidence level, 95% confidence level, we got Z equals 1.96, and we've got X bar is 108.6, N is 100, and sigma conveniently is 15. But we're going to assume that that's actually taken by a sample, so little s is 15. So subbing it in to our formula, we have 108.6 minus 1.96 times 15 over the square root of 100, which is 10, and the same expression with a plus sign in the middle. Okay, and whoops, close your bracket properly, and that suggests we have to two decimal places. We have 105.66 up to 111.54, so we have a 95% level of confidence that the mean is in that interval from 105.66 to 111.54, which is an IQ. For the sample size of 400, if you plug that in, and the only thing that will change is n, so try it yourself and you get 107.13 up to 110.07. Now look at that there, we have a narrower So narrower interval when we have n equals 400, so it's narrower than when n equals 100. That's related to the increased certainty with a larger sample size. So if we have, going back to n equals 100 at the 90% confidence level, we can put those figures in, okay, and that will be 108.6 minus, now the quantile is 1.64 for the 90% level, and we had 15 over the square root of 100, which is 10, and likewise at the other end, 15 over the square root of 100, i.e. 10. And my calculations give 106.14 up to 111.06. And we're going to try also the 99% confidence level. Okay, and putting that in, I get 104, using the same process, 104.73 up to 112.47. So let's compare those now. So highlighting the three confidence intervals that were based on n equals 100. There's 1, there's 2, and we had 1 just up here. Okay, so we have, so from the lowest confidence here to the mid-level and to the highest, what do we notice? Well, 90% compared to 95, so the interval is wider from 90 to 95, and the interval is wider again at 99%. And so what we get then is increasing confidence means a wider interval. And that's a trade-off that I've mentioned in a previous video, which is based on population proportion, the same concept. So increasing confidence means you need a wider interval as a trade-off. If you want to be more confident, you need a wider interval. Final example, now for something really exciting, paper clips. So a stationery factory claims that they fill their premium paper clips. Now, wouldn't this be a great place to work? Premium paperclip packets. They're claiming an average, it's printed on the side of their packets, 180 paper clips average. Quantity surveyor, however, thinks, I might conduct a random sample. I'm going to take 120 packets and I'm going to go away and calculate the mean and standard deviation, and this person does that. They get a sample mean of 171.5 a sample. This is a sample standard deviation, right? So that's little s. It's not assumed. We do have a sample standard deviation that this person calculated. It's 7. And we've got to evaluate the reasonableness of the factory's claim by applying a 99 confidence interval level. Alright, so I'm going to show you this way with the formula and also some graphics calculator functions you may wish to make use of in a TechActive question. Putting in the appropriate values and then calculating, I get 169.85 up to 173.15. And to check with technology, you can do the following. So we go menu on a TI Nspire, menu statistics, and then statistics, confidence levels, intervals, confidence intervals, and Z interval. We're working with Z standard, and change it to statistics here in data input. Okay, now it starts with the standard deviation, okay, and that's not S. Alright, that's the population standard deviation, which is 7, so be careful, try and remember that. Okay, and yet it does ask for X bar, the sample mean. Alright, so it's actually the sample mean and the sample standard deviation Alright, even though it says sigma is what I meant to say there. Okay, and remember, if n is greater than 30, which it is, it's 120, we can assume that sigma is s and s is sigma. Okay, so we've got 171.5 there, and n was 120. Now we have to type in the level we want, 0.99 for the 99%, and do we get the same thing, 169.85 and 173.15? Indeed we do. Good stuff.